This is a lecture about the prime numbers. So a prime number is an integer n greater than or equal to 2 whose only divisors are plus or minus 1 and plus or minus 2, plus or minus n. And a composite number is a number that's not a prime. It is an integer n greater than or equal to 2 that is not prime. So every integer greater than or equal to 2 is either a prime or composite. You might ask about 1. Well, 1 is neither prime nor composite. And it's very interesting to try to find prime numbers, even to list them. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, hope I'm not skipping any, 31, 37, 41, 43, 47, run out of space. Well, those are all prime numbers. I don't think I've left one out, but have to check. And prime numbers are like the atoms in the periodic table. Just the way every chemical molecule is composed of atoms, every integer is a product of prime numbers. In particular, I should call this a prime factorization of n, is a representation of n as a product of prime numbers. And what is called the fundamental theorem of arithmetic says that every positive integer is a product of prime numbers, and not only that, in a unique way. So if we start to write the integers as products of primes, 2 is 2. It's a product of 1 prime. 3 is 3. 4 is 2 times 2. 5 is 5. 6 is 2 times 3. Of course, you might say, well, you can also write 6 as 3 times 2. And when we say unique, we mean unique up to order. So if you write a number as a product of primes in 2 different ways, then all you have is that one way of writing the product is some permutation or rearrangement of the primes in the other product. 7 is 7. 8 is 2 times 2 times 2. 9 is 3 times 3. 10 is 2 times 5. 11 is 11. 12 is actually a lot of fun. 2 times 2 times 3. 13 is 13. These are all the factorizations of the integers as products of primes, and so on. And in fact, it's a very hard problem in computer science to write a computer program that will factor an integer in a reasonably efficient way. It is one of the great unsolved problems in computer science. Well, half of the fundamental theorem is easy to prove. Every integer greater than or equal to 2 is a product of prime numbers. And we can give a proof by induction on n. We can start with the case n equal 2. 2 is a product of prime numbers. It's a product of 1 prime. So suppose n is some number greater than or equal to, well, let me say, suppose n is greater than or equal to 3, and every integer less than or equal to n minus 1, well, let me do this the way I usually do this. Suppose n is at least 2, and every integer less than or equal to n is a product of prime numbers. So consider the integer n plus 1. There are two cases. If n plus 1 is some prime number, p, we're done. If n plus 1 is composite, then it factors. That means that you can write n plus 1 as a product of two numbers, called n1 times n2, where n1 is less than or equal to n, and n2 is less than or equal to n. Well, n1 less than or equal to n, and means that n1 is a product of some prime numbers. And n2 less than or equal to n means n2 is some product of prime numbers. So n plus 1, which is n1 times n2, is p1, product p1 up to pk, q1 up to ql, and this is a product of k plus l primes. So we're done by induction. Take an integer. Suppose every number up to a million is a product of primes. Take 1,000,001. If it's a prime, we're done. If it's not a prime, it factors. And each factor is less than 1,000,001. So each factor is a product of primes. You concatenate them and you have your result. So that's the proof of the easy half of the fundamental theorem of arithmetic. Every integer is a product of prime numbers. What remains to be proven is that every integer is uniquely a product of prime numbers. And for that, we need to go back to Euclid. Now, before I prove, there's a lot in Euclid that's not geometry. In particular, there's a lot in Euclid which is number theory, arithmetic, algebra. And Euclid proved that there are infinitely many prime numbers. This is truly one of the great results in the history of mathematics. When I started to make a list of primes a few minutes ago, I went up to about 53 or so, and it might be at some point it stops, there are no more primes, or it might be that it never stops. No matter how large a prime you choose, there is always a larger prime. So it's the latter that is the case. And so here is a proof of Euclid's theorem that there are infinitely many prime numbers. This is really, I should put a little box around it and give it a star, because this is really an important result. So it suffices to show that if you have a finite set of prime numbers, P1, P2, up to P sub k are primes, then there exists a prime, I'll call it Q, which is different from all of these, not equal to P1, not equal to P2, and so forth, not equal to P sub k. And how do we prove this? Well, suppose we let capital N be the number that we get by multiplying this finite set of primes together, P1, P2 up to P sub k, and adding 1. So we have an integer n greater than or equal to 2, and every integer is a product of primes. So there exists a prime Q that divides n. Well, if n is equal to P sub I for some I between 1 and k, then what do we have? If we rearrange this equation, we get 1 is equal to n minus P1, P2 up to P sub k. Now, P sub I is one of these factors, so Pi divides this. So there's a prime Q that divides n. If this prime Q is one of these P's, Q divides n, which is some Pj. Pj, Pi divides n. This number is divisible by Pi. This number is divisible by Pi. This implies P sub I divides 1. But that's absurd. 1 is not divisible by anything bigger than 1. So that's a contradiction. So therefore, Q is not equal to P sub I for all I. Okay. I'm going to go through that proof again because it is so important. We want to prove there are infinitely many prime numbers. And we prove it by contradiction. Or equivalently, what we're going to do is the following. If you give me any finite set of prime numbers, P1, P2 up to P sub k, I'm going to prove there's another prime that's not on this list, which means the total number of primes cannot be finite, because if it were, you could give me the finite list of all primes, and I shouldn't be able to construct a prime not on that list. So here's a finite set of primes. Multiply them together and add 1. So that's a positive integer bigger than 2. Every integer greater than or equal to 2 is a product of prime numbers. So there's some prime Q that divides n. So Q divides this capital N. If Q were equal to one of these primes, it would also divide this product. So if the prime Q divides this and this, it divides their difference, which is 1. But 1 is not divisible by a prime. That's a contradiction. So Q is a new prime. And that is a proof of Euclid's theorem. Now, to prove the uniqueness part of the fundamental theorem of arithmetic, we need 2 results, which are both lemmas due to Euclid. This is the first form of Euclid's lemma, or Euclid's lemma 1. It says the following. Suppose you have integers a, b, and m with the following 2 properties. M divides the product of a and b and the greatest common divisor of A and M are 1. The conclusion is that M has to divide B. And the proof is as follows. If the greatest common divisor of A and M is 1, then, and we proved this in the previous lecture, there exist integers, x and y, such that ax plus my is equal to 1. That's very important. So multiply this equation by b. We get abx plus mby equals b. We're told that m divides ab. So ab is m times q for some integer q. So if I substitute that in here, we get mqx plus mby equals b. And I can factor out the m. This is m times qx plus by. So m times some integer equals b. So therefore, m divides b. That's the proof. It didn't take a huge amount of time or space to prove it, but there are a lot of algebraic ideas in this proof, and you do need to spend a lot of time to understand the proof. So this is the first version of Euclid's Lemma. If m divides a product of two numbers and it's relatively prime to one of them, then it divides the other. And the next form of Euclid's Lemma is a generalization of this. Suppose you have a prime number p, this replaces the m, and you have k integers a1 up to ak. If p divides the product of all these numbers, then it has to divide one of them. So if a prime divides a product of integers, it must divide at least one. Okay, well, what is the proof? So we can say if p divides the number a sub k, we're done. If p does not divide ak, but we know p does divide, I use a vertical line, that means division, a1, a sub k minus 1 up to a sub k. We know p divides this product, which we can think of as the product of this number and this number. And by the first form of Euclid's Lemma, if p doesn't divide ak, but it divides the product, it divides this. So therefore, p divides a1 up to a sub k minus 1. And we repeat the argument. If p divides a sub k minus 1, we're done. Otherwise, see, a sub k minus, this is like a1 up to a sub k minus 2 up to a sub k minus 1. If p divides this product and it doesn't divide this factor, it divides this factor. And we just continue step by step, knocking off factors until finally we get p divides a sub I for some I. So this is one form of the proof. It's very nice. So this is the second version of Euclid's Lemma. If a prime number divides a product of integers, it must divide at least one of them. Could divide more than one, but it must divide at least one. And now we have all the tools we need to prove the fundamental theorem of arithmetic. Every positive integer can be written as a product of prime numbers in a unique way. So the first part of this I've already done. We proved that every integer n is a product of primes. What we have to show is uniqueness. So suppose n is a product of the primes that say p1, p2 up to p sub k, and it's also a product of primes q1, q2 up to q sub l. So I claim, first of all, that the number of primes on both sides is the same, and after you rearrange the numbers, because 2 times 3 equals 3 times 2, pi equals qi for all I. Okay, well, let's see. pk, here it is, divides n. So pk divides q1 up to ql. But if a prime divides a product, pk divides qj for some j. So qj is equal to pk times some number d. But that implies that qj is actually equal to pk because qj is a prime. It doesn't factor. So I can cancel it from this expression. And I get p1 up to p sub k minus 1. Let me just renumber the things on the right. Is q1 up to q sub l minus 1. And then step by step, I can cancel primes until finally I end up with 1 equals 1. And again, this requires a little bit of thinking, or maybe a lot of hours of thinking. And the proof is also in the textbook. But this is a proof of the fundamental theorem of arithmetic. And a lot of abstract algebra is based on efforts to extend this theorem and generalize it to other situations. And when it doesn't generalize to other situations, understand why not. Okay, that's all.